So in the last class, we have discussed about the electromagnetism and the fundamental ideas of electromagnetism, how electromagnetism is defined, electric fields and magnetic fields, and how they interact with each other. So today we'll be talking about the vector calculus. The main reason for this is that we need to have a background understanding about vector calculus to do the computations related to electromagnetism and understand the system. So therefore, we need to have an understanding about vector calculus. So in the last class, we discussed about what electromagnetism is, and we defined it as the study of the interaction between the electric field and the magnetic field, which are generated by charges, electric charges, and currents. Just produce electric field, and currents produce magnetic field. Next, so that brings us to the question: what is a field? Right? So field is defined as a region, right? A region where a certain parameter is defined at each point in that region with respect to space and time. Okay, so field is defined as a region that has a certain parameter which is having a certain magnitude and a direction if it is a vector field, and the total, space we call as the total region we call as a field, right? So this field, this region with having some physical parameters, we that can be defined with respect to space, that means with respect to the location, and the time we call as a field, right? So the physical quantity can be a scalar or a vector, right? So what are the physical quantities as examples, right? If we take temperature, for example, in a certain region of the environment, we can define a certain region, right? And then we can define a temperature at each point in that region, right? The temperature level could be different, but each point will have a certain value of temperature, right? So it could be 5 Celsius, it could be 2 Celsius, could likewise at each point we can define the temperature, right? And also this temperature will depend on the time, right? So once we take the temperature, if we take the temperature measurements at 1 p.m., the temperature values will be a certain set of temperature values. However, if we take it at another time, right? If we take the temperature values at 6 p.m., the temperature distribution in this region, the temperature values in this region will be different, right? It might not be the same values, right? So therefore, these parameters in a field are defined with respect to both time and space. That means location, right? So and based on the time we consider the physical parameters that are defined over a certain region, and that region is what we call as a field, right? And then now this is temperature is a scalar or vector, right? Can you answer? Is the temperature having a direction? Do we call scalar, right? So it is it's the scalar. So it doesn't have a direction. We don't say that temperature is in the east direction or in the west direction. We don't tell like that. We don't specify a direction to the temperature. So likewise, we can define parameters such as temperature, humidity, uh, pressure that we measure has the, magnitude only. So they are called scalar parameters. And therefore, the regions which can be defined, using these scalar parameters, we call as scalar fields, right? The field with the temperature measurements, we call as the temperature scalar field, right? So humidity, pressure also, we can define like that. So similarly, we can also consider vectors, right? If the vector parameter that we consider is in a certain region, and we can define the parameter, the vector parameter at each point in that region and at a certain specific time, we call that a vector field, right? So in electro, not about vector fields such as electric field, right? Electric field and magnetic field, right? So these fields define how how much of a electric force is there at each position in the field. So if we take a field, the electric field will define how much of a electric force is there at each location in that field, right? With a magnitude and a direction, right? So the electric force will be a vector. So therefore, the parameter will be defined as a vector. So therefore, it will have a certain direction, right? So depending on the charges around it, electric force on a certain point in the region is impacted by the neighboring charges, and the total impact is taken as the total electric force on that point in the region, in the field, and that total force is defined as the electric force at that location. So the electric force can vary from point to point based on the electric charges that are around them, right? So the electric field will be defined like that, right? So the electric field will be consisting of vector components. So then what is the difference between scalar and a vector? Right? What is the difference between a scalar and a vector quantity? So does the scalar has a direction?
No.
No, right? The scalar has only magnitude, and the vector, it has both the magnitude and the direction, right? So that is the main difference between scalar and vector quantities, right? So that once we take the difference between scalar and vector fields, the difference there is that the scalar and vector fields, in scalar field, the field is defined by scalar parameters, scalar physical parameters, right? So scalar is a quantity that has both magnitude and direction. So the examples of scalar quantities will be mass, density, pressure, volume, voltage, and so on. And the examples for vector quantities will be electric force, magnetic force, velocity, acceleration, and so on. Right? So the difference between the scalar and vector field is basically that the quantity, physical quantity that we define in the region is a scalar in the scalar field, and the quantity is a vector if it is a vector field. Have in vector algebra, we have some laws, right? So do you know what is the commutative law? So this is basically mathematics. So the commutative law says that once you like reverse the order of the addition, for example, right? The vectors, the resultant of the addition will not change, right? So if we add the vector A with to vector B, it will be same as adding vector B to vector A, right? So the vectors follow the commutative law. Of the multiplication, it might not be true all the time, right? So A into B might not be equal to B into A, right? I mean, once you take actually dot product, actually we can take them as equal because that is a scalar output. However, in terms where we are taking cross product, right? When we are taking the cross product, these are not equal. And therefore, we don't normally say the product between vectors are equal to the, commutative product of the vectors. I mean, once we change the order of the vectors, the product, once we take the product between those vectors, and once we change the order of that product, those two might not be equal at. Okay, so if you have any questions, please let me know. I think this is a mathematics actually content. And then associative law, right? So associative law means that once we do the vector addition, for example, using, two vectors first and then doing addition with the rest of the vector, it will be same as grouping the another set of vectors and then adding to the rest of the vectors. So grouping of vectors and then doing the addition with the rest of the vectors do not affect the final output of the vector addition, right? So I will B plus C grouped is equal to A plus B grouped plus C. So the resultant will not change based on the grouping of the vectors we do in the collection of the vectors. And then so the first one, the commutative law, is saying that in vectors, basically we can say that the order of the addition does not affect the result, right? So for addition, we can directly say that vectors follow that rule. And once we add two vectors, we can also get same result once we change the order of those vectors. Then once we talk about the coplanar vectors, so coplanar vectors are vectors that lie on the same plane, right, in a three-dimensional space. So if we have a three-dimensional space, if we take a x, y, z coordinate system, this is a three-dimensional space, right? So if we consider a plane which is in the xy plane, right? So if I take a plane which is parallel to the xy plane, right? So, right, so we will consider that this plane is parallel to the xy plane, right? So this plane is not not having not parallel to the z axis. So this is um, plane which is parallel to the xy plane, and once we have vectors in this plane, right? Once we have vectors in this plane, uh, that those vectors we call as coplanar vectors, right? So the vectors which lie on the same plane, right? So in a three-dimensional space, once some vectors are lying on a certain plane, we call that coplanar vectors, right? So sometimes the vectors, I mean, they are actually only in that plane, and not uh, they are not related to the z axis, right? In this specific example, right? So if we have a certain vectors which are lying on the same plane, we call that coplanar vectors. And can you tell me what are the two main methods of doing vector multiplication?
Cross product and dot product.
Yeah, so the main the main methods of doing vector multiplication is a dot product and cross product. So dot product we can define using the magnitudes of A and B vectors and the smallest angle between those vectors, right? So once we take uh, the cross dot product, and once we have two vectors, and we have A vector and B vector, we can find the dot product between these two vectors using the magnitude of these vectors and the angle between them, right? So this is a standard, and we need to follow that standard when we find the value of the dot product, right? So dot product is used basically in situations where we need to take the projection of a vector on another vector. So in here now A vector, I mean A vector is there, and then we have the B vector, right? So B cos theta, right? Once we take the endpoint of B vector as this, once we take the projection onto the A vector, we can write that magnitude as B cos theta, right? So in here, we have taken the projection of a vector on another vector, right? And also we have considered the magnitude of the A vector as well. So the projection plus the magnitude of that A vector we have taken into consideration once we take this product, right? So this is useful in situations where we are calculating the work done by a certain force along a certain direction, right? So if we take the force as the vector B, once we have the projection on the vector A, we can find the component of the force, right? If we take this as the force, the component of the force along A direction is F cos theta, right? So, however, this force also need to travel the magnitude along the vector A, right? If we consider that the F cos theta is applied over the A vector, then we need to take the magnitude of A and take the product with the F cos theta to take the total work done over the the vector A. So anyway, this is basically used in mathematics to find the work done by a certain force, right? So that is the kind of important application of dot product. Next, we can discuss about the cross product. Apart from that, is the dot product scalar or vector? Is the output of the dot product a scalar or a vector, as you think? So, as I've explained to you, the product here is based on the magnitudes of the vector A and B, and then the cos theta value, right? There's no direction vector added here anywhere, right? So therefore, the dot product output will be a scalar. And then dot product properties, right? Once we take the dot product properties, we have actually multiple properties. So we can actually consider basically two properties in here. As I mentioned before as well, the dot product will follow the commutative law, right? So the dot product will follow the commutative law, and the uh, uh, once we change the order of the vectors, it does not change the output of the product. So that means like once we change the order of the product to B dot A, then the by definition we can get the output using B magnitude A magnitude into cos theta. The same operation will be done again, because we can take again A to the front, and then we can write this, and we can get the same output as before, right? So therefore, we can see that the B dot A is equal to A dot B. Apart from that, the another factor feature is that the dot product of a certain vector with its own vector gives the magnitude squared of that vector, right? So that means that if we take the dot product of a certain vector with its own vector, then its definition will be A into A, right? Cos, what should be? What should be the angle? Understand what I'm asking? So if we are taking A, the vector A, and we are taking the product with its own vector, right? Then the angle between those two vectors, right? If there are two vectors which are similar, right, which are known as A, then we can consider that those two vectors lie on the same line and at the same point and on top of each other. So they overlap, and there's no angle between them. And therefore, the theta angle will be 0, and therefore the cos theta here will be cos 0. Therefore, the magnitude will be squared. Vector magnitude will be squared. So once we take the vector with its own dot product of the vector with its own vector, then the magnitude squared will be taken as the output. Right, so if you have any questions, please let me know. So next we have the cross product of A and B. So did you learn about cross product before? Do you know the definition of cross product? Have you, do you know whether it's a scalar or vector? Can you hear me? Okay, so the cross product of A and B, right? So it is very important product operation that we can take, right? So A and B cross product can be calculated by using the magnitude of A and B vectors, the angle between those vectors, and the unit vector, which is going in a perpendicular direction to both A and B. Right. So once we take the unit vector along the perpendicular direction to both A and B, we can call that as n hat, the unit vector along the perpendicular direction. We can call it as n hat. Then we can define the cross product of A and B using the this equation, right? So A into B into sine theta into n hat. So the sine theta is the difference between, the cos, in dot product, we use the cos theta. In here, we are using the sine theta. And also we are adding this unit vector, which gives us a direction along which the output is lying. Right. So this is important in many cases, and especially once we are learning about the wave propagation, right? We need to find the direction of the wave propagating once we know the direction of the electric and magnetic fields. So if we know the direction of those two fields, then we can find the wave direction, the direction of the wave using this cross product. So therefore, we need to know these products. And then the cross product, as you can see, is a vector, right? So this is like a vector magnitude. This is also scalar. This is a magnitude is a scalar. So all these are scalars. However, this unit vector makes it a vector, right? So apart from the dot product, the unit vector added here, right, will make this a vector, right? So the cross product is a vector. So we can define the cross product using these equations, and we can say that the output of the cross product is a vector, right? Then, so how can we find the direction of the cross product, right? So that is a very good, I think a good question, because actually the cross product gives us uh, both the magnitude and a direction, right? The cross product of two vectors give both a magnitude and a direction. So therefore, once we are using the cross product between two vectors, we can find the resultant vector using the right hand rule, right? So the right hand rule is useful in finding the direction of the cross product. So what you need to do once you want to find the direction of the cross product, right? You need to use the right hand rule, right? So what is the right hand rule, right? So it's actually, during this online class, it's difficult to show by pictures, but first you need to turn your fingers from the starting vector to the ending vector, and the direction where the fingers pointing is the direction of the resultant vector, right? So in this figure, it is shown a case where we take the cross product between A and B. So we first need to start from the vector A, and then we need to go to vector B. So once we keep our fingers, the fingers in our right hand along the direction of A, and then move towards B, the direction where our thumb is pointing is the direction where the A cross B lies. So, right, I will try to draw this using fingers, right? If it is this, if my finger is along direction of A, and then I turn it into the direction of B, right? If I turn it into the direction of B, my thumb will be pointing in the direction like in the bottom direction, right? If my hand is moving from A to B, the thumb will be always pointing down, right? So I will ask a question from you. What is the direction of B cross A? Can you tell me? You can let me know in the chat also. Yeah, it's perpendicular up. I mean, in the z-axis direction, right? In this direction, right? It's in top direction, right? So likewise, you can actually find the direction of the cross product, right? So this is essential in situations where we want to find the direction of a wave propagating. Once we know the direction of electric and magnetic fields, right? So the electric field we normally denote using the capital letter E, and the magnetic field we can denote as using the capital letter H, right? So in this case, what is the direction of the wave propagating? Right, the wave propagating direction is given by E cross H. So can you tell me what is the direction of the wave propagating in this situation? Yeah, it's along the right. So it's correct, right? So you keep the finger in the E direction, and then you turn the fingers along uh, from the E direction up to the H direction, where your fingers will move like towards you, and then the thumb will be pointing in this direction, right? So therefore, we consider that, I mean, we actually can see it as well. We can easily find that the wave is propagating in this direction, right? So once we are actually designing antennas, some other equipments that require the wave propagating, and when we want to propagate our wave in a certain direction, we need to consider these kind of principles to find like in what direction the wave will propagate, right? If we know the direction of the electric field and magnetic field, which are produced by voltages and currents that we supply to the system, then we can actually find the wave propagating direction, right? And that is the kind of the application of the cross product, right? And next, the cross product properties, right? So the one of the special properties of the cross product will be this, right? So if we have a certain vector, certain unit vector, and this also a certain unit vector, right? So along y-axis, and this unit vector along z-axis, then the resultant will be a unit vector along x-axis, right? So what do I mean, right? So if we take a Cartesian coordinate system which has x, y, x, z coordinates, I mean axis, we can take that the unit vector along this x-axis as I hat, right? And then we can take the unit vector along the y-axis as j hat, right? So once we take the cross product between I hat and j hat, right? If the unit vector along the z-axis is k hat. Right? If it is k hat, what is the cross product of I hat into j hat? What is the output? K hat, right? Yeah, it's correct. So k hat. What is the, I mean, k hat into I hat? What is it? It's j hat, right? So likewise, the once we take the cross product between two unit vectors which are perpendicular to each other in a situation, will point the output in the perpendicular direction, and it will be a special case in this system where the output will equal to the unit vector along the uh, remaining axis direction. Right, so then we are we will be actually learning vector operations next. So I will move on to that as well. So anyway, after vector operations, we will be talking about coordinate systems, because coordinate systems are very essential for us to define electric field and magnetic field with respect to space and time, right? So with respect to space and time, we need to define the electric force and magnetic force and likewise, right? So therefore, we need the knowledge of the coordinate systems, and therefore we need to discuss about the different, coordinate systems that are commonly used in electromagnetism. Right, so these coordinate systems were first introduced by a person called René Descartes. He was a French scientist, and then he was the first person to graphically show a certain parameter moving in the space. And he was the first person to introduce the idea of graphs, graphically representing something. Right, so therefore, this he's known as the person to introduce the coordinate system into this world. So therefore, he's actually known for that, right? So we'll be learning about coordinate systems, and we will be basically looking at three types of coordinate systems, which are Cartesian and cylindrical and spherical. Right, so you might ask, why do we need to have all these coordinate systems? Right, so these coordinate systems are used depending on the application. Right, so based on the application that we are using it on, we will choose the best coordinate system to uh, use in that situation. Right, so based on this type of coordinate system we use, the calculations will be easier. Right, sometimes rather than using a Cartesian coordinate system, if we use the spherical coordinate system, the ability for us to compute the complex mathematics will be more simplified. And rather than using spherical, sometimes even Cartesian will be better in situations. Right, so we will actually discuss next about the vector operations. Right, so vector operations, we can talk about the vector operations, right? So that is another like aspect of vector calculus, right? So we discussed about the vector products and how they are defined and what are vectors and so on. So apart from that, we also need to use some operations on the vectors which are specifically defined, in a certain using a certain mathematical notation, right? So we will discuss about each of these vector operations, right? So these will be like required for us in order for us to understand the electric field and magnetic fields and how they will be behaving in a certain medium, right? So the vector operations such as gradient, divergence, Laplacian, curl will be useful for us. So therefore, we will be looking at the definitions and the behavior of such kind of operations. And also we'll be learning about why we need those operations as well, right? So once we talk about the gradient operation, we can actually define the gradient operation using this equation, right? So you can uh, just study this equation, right? So this equation is saying that once we are given a certain um, field, right? A certain field, right? With which is defined using x, y, and z coordinates. So x, y, z parameters, if a certain function that define the field is given, right? We can apply this gradient operation on that function, and we can find the gradient of that function, right? So this gradient of that function is giving some important parameter regarding that function, right? So once we find the gradient of that function, we can find the direction of the steepest descent of that function at each point in the space, right? So the steepest ascent of that function at each point in the space. So that means that if we have a function like a mountain, right, which is shaped like a mountain, and if we take the grad of that mountain at a specific location, that mountain, the grad operation will show us the direction of uh, of the position, direction to which the maximum point is happening in that function. That means that if there's a maximum in that function somewhere, the gradient will show us where the maximum is, in what direction the maximum is. The function will have a certain maximum, and the gradient will show us where, in what direction the maximum will occur, right? So the grad is, defined like this, right? So you need to take the derivative of the function that we are given with respect to x, and then we need to multiply by the I hat. And then we need to take the respectively derivative with respect to y, and we need to multiply by j hat. Next, with respect to z, then multiply by k hat. Likewise, we need to do that operation. Then finally, are we getting a scalar or vector, as you think? Right? So can we do the first one? Yeah, we will get a vector, right? The reason is that I hat, j hat, k hat are vectors, right? Once we take the gradient of this field, right, with respect to x, right, with respect to x, and then multiply by I hat, and then right, then we multiply by I hat, right? Then we take the derivative of x squared with respect to y, and then we multiply by j hat plus the derivative of this x squared into k hat, right? So what are these terms? What is the output of these terms? 0, right? So we can take these two outputs out of our calculations, right? And we are only left with the derivation of the x squared with respect to x. right? So therefore, what is the output? Yeah, 2x into I hat, right? So therefore, we are actually having both the magnitude and uh, the vector component, right? So this is a vector. Next, we can do the similar thing for the this function as well, right? So can you find the answer to this one? Yeah, so that's correct, right? So 2x I hat plus 2y j hat plus 2k, I mean 2z k hat, right? So likewise, we can do like that for each of these functions. Oh, what is the answer for this? If C1, C2 are constants, what is the answer? Yeah, C1 I hat, because the derivative of x with respect to x will be 1. So C1 I hat plus C2 j hat plus C3 k hat. So likewise, we can do those calculations, right? So it's good that you understand. And then we can uh, move to the next operation, right? So uh, the divergence operation, right? So we will also actually, if you want, I can talk about this in the next class as well. I will give a just understanding about the divergence operation, and I will explain why it's important. And the divergence is a very, I mean, important operation in the electric field and magnetic field domain. And once we are deciding the amount of electric field across a certain surface, right? So if we have a certain surface, right, in here it is given as some cuboid, a cube, and if there's some, like flux electric field lines that are going from the surface, that are moving through a surface out, and uh, due to a certain charge that is staying inside of this volume, right, that the electric field lines that are going across a certain area, we call as the electric flux, right? So the amount of electric flux that move along a certain unit area, we can find using the divergence operation, right? So once we know the, for example, the distribution of the charges, we can find the total electric flux across a surface, right? So once we know the electric flux across a surface, we can actually understand the amount of electric force that will be that is generated around that area and around that volume. And therefore it is essential for us to know the operation of divergence. And once we are given a certain field, right, if we are given a certain field which is defined using the function a, and we can find the divergence by taking the dot product between the field and this term, right? So we have this term which is I hat into dabba over dabba x, right, plus j hat into dabba over dabba y plus k hat into dabba over dabba z. So this is similar to the grad operation, right? So in grad operation, we had this same operation used, right? So apart from the grad operation, now we are taking that grad operation equation with the dot product with another function, right? So once we take this kind of a dot product, is the output a scalar or vector, right? If we take a divergence of a vector, it's a scalar, right? So it's really good. So you know that once we take a divergence of a vector, if it is I hat plus j hat, for example, if once we take the dot product between these two vectors, right? We can take the dot product of I hat into I hat as one, right? Because the magnitude is one. So therefore, we be only left with this term. Once we take the j hat, I mean dot product between j hat and this j hat, then we are only left with this term. So k hat, there's no k hat term in here. So therefore, it will be anyway equal to 0 because there's no component of k hat in here, which should be 0. So 0 into the magnitude here will be anyway 0. So this component will be 0. And whatever the remaining components will be scalar. So therefore, the output of the divergence will be a scalar value, right? So that would be something that we can remember. Okay, so can we find some divergence of some these kind of functions, right? So first I will do the first one. So we define that dabba over dabba x I hat plus dabba over dabba y, right? I mean j hat plus dabba over dabba z k hat dot product with xi, right? So since we are taking the dot product here, the value of the dot product with another like perpendicular unit vector will be 0. These will be 0. So the only component that will give us a value is the dot product between the dabba over dabba x into x, right? So that will be dabba over dabba x into x and into 1, right? Because I dot I will be 1. So therefore this will be equal to 1, right? So can you do the second one? So the second one's the answer will be dabba over dabba x into x squared, right? Plus dabba over dabba y into 3y, I mean cube of 3, right? Plus dabba over dabba z into z, right? So this will be equal to 2x plus 3y squared plus 1, right? So this is actually, yeah, your answer is correct, right? So similarly, we can do for other functions as well. So for this function also we can do, right? So it will be easy, I think. Third one. Yeah, it will be 3, right? So this will be equal to 3. So you can take the derivative of x with respect to x, y with respect to y, and z with respect to z, and then you add them all. It should give you 3. And so I think it was a very mathematical, lesson today. So apart from that, I have some more vector operations, right? So I will do them slowly in the next class as well. So in the next class, we'll be talking about the Laplacian operation and how it's defined and how we can find the Laplacian of a certain, function. And then we'll be talking about the curl operation. And with that, I think the operations will be finished. Once we talk about the operations, we will be next moving towards the coordinate systems. And then we'll be learning about the different elements in the coordinate systems, and we will be able to understand the coordinate systems, right? So I hope you learned something. If you have any questions, you can let me know, right? So I will actually stop the recording.